Okay, welcome. So this is lecture 21, and the announcement, well, simple announcement, assignment 9 has been uploaded, and the deadline is next Monday. And the next assignment, assignment 10, will be uploaded this Friday, and the deadline will be, well, I will set it, I'll give you a little bit longer. Okay, so it will be maybe on the Wednesday rather than Monday after. And then the midterm answer books can be collected. And I think there's a slot today. So just after this lecture, you can come to me if you're around, or you can collect from, I think it's still me. You can collect from me on Friday. Okay. And well, all the time slots have been announced, so you can check the email for the details. Okay, and you should have received the midterm score on Blackboard. I checked with a few of you earlier, so you should be able to see those. Okay, any question? And remember, the number you see on your screen is not the percentage scale. You have to divide by 68, okay? And yes, I will give you the statistics later at the end of today's lecture, okay? All right, so I want to continue what we discussed last time. So last lecture, we derived this distribution, this important statistics, quantum statistics, and this is from last lecture. And the important point is to there were many important stuff, and you are required to learn how to get to this point. So you started by looking at how to come up with different ways to distribute the fermions or the bosons in the energy states, right? GK levels, you have GK states, NK particles, and how do you do that? So we started from there, and then we applied the usual procedure to get to this point, okay? So the key difference is this minus and -1 and +1. And this tiny difference actually make a huge difference. And please remember which one to use. This is something I think as a student of this course, you really have to really remember this. Okay, if you use the wrong statistics, imagine in the exam, if you are asked to calculate something, and if you use the wrong statistics from the beginning, the whole calculation will be meaningless. Okay, so you need to really remember how to derive, and better try to come up with a way to memorize this difference, this +1 or -1. I told you how to do that last time. If you are not sure, go back to my lecture on Monday. There's a video available for this. Okay, and if you are in the dilute limit, there's no difference between boson and fermion because they do not really have the chance to compete for the same energy state. And therefore, the difference of -1 and +1 becomes not important in the dilute limit. And therefore, to get the classical statistics, you can just ignore this constant here. Okay, there was one way to do that, and the other way is to argue that in the dilute limit, you simply have this ratio to be very small, and therefore this denominator has to be very large. And when this is very, very large, you don't have to worry about this tiny offset of +1 or -1. That's why you get your Boltzmann factor again. Okay, so today is we are going to use the red one, the bottom one, the Fermi-Dirac. Okay, so this is from the last lecture, exactly the same slide. As a motivation of why we need to we need to know about electrons in metals. And I think I will just highlight what you need to keep in mind. So today, we want to explain this phenomena. Okay, we want to explain why such a heat capacity is not observed. So this is the prediction from classical physics, if you like. It's an ideal gas treatment, kinetic theory of gases. And you already know how to get this if you have a monatomic gas. We did it last time. We did it several weeks ago, and then I reminded you again on Monday, so you know how to get this. Okay, so if you just follow Judah and he used this treatment, just really copy and paste from the physics of gas and write down this. And the problem is such a huge heat capacity due to electron is never observed. So this is too large, and never seen in experiment. Okay, so this is, if you follow this, today we are going to introduce some machineries, and towards the end, I hope this is the puzzle that I can solve for you today. Okay. All right, let's start. So here I give you the Fermi-Dirac distribution right away. So here again, this is +1, and I will try to give you the equation numbers you need. And we are going to assume right away that we have a very closely spaced energy level. So energy levels are closely spaced, and therefore we are going to use the continuum limit. Okay, so closely spaced energy levels. Okay, so we can write this F. So I'm going to label it for you here, but then I'm going to drop the label later. Okay, so I think, yes, today we are not going to talk about Bosch-Einstein. So when you revise, please make sure make sure you know what I'm talking about. Okay, so this is a Fermi-Dirac. So this is usually called the Fermi function, but I think we should give Dirac a little bit of credit. So this is a Fermi-Dirac function. Okay, FD, Fermi-Dirac. Okay, so in the continuum limit, this n is become a function of epsilon, and then you have this GEDE. Okay, and we would just have to quickly write this down. And this is epsilon minus mu, where mu is the chemical potential, KBT, minus 1. Sorry, plus 1. Okay, so this is a very simple rewriting of this function in the continuum form. Okay, so here this is something we derived before in chapter 10, and we derive without this blue factor here. This is something I add in simply because back then when we saw for these energy levels, remember how we get this? We got this from this is, by the way, this is the density of states in energy. Okay, G of E, and we obtain this from a specific energy function. So this is this comes from E, this kinetic energy form, and then we take the particle in the box problem, analyze it, and then we use the box boundary condition. and we obtain after quite a few lines, we obtain this. Okay, so this is it's not something new here. Okay, so maybe I should just note that if we use periodic boundary condition, which is something I would do today, periodic boundary condition, this is something I haven't done, but it's not that new because TA did it in the exercise class. Okay, I did the box and TA did the periodic boundary condition, and today I'm going to use it again. I just want to say that periodic boundary condition gives you the same result here, which is important. There will be some differences in the way we derive things, but the end result is the same, which is good. So gives the same result. Okay, so this is G of epsilon, D of epsilon tells you the number of states between epsilon and epsilon plus D epsilon. Okay, so this is the meaning you should always remember. So this product, if you take this whole thing multiplied by D, that gives you a number. Okay, so there we solve for those states, and now we want to just pick that picture and use it to describe the electrons. And how do we do that? We need to remember that we have the spin degeneracy. That's to say, you can have all other quantum numbers to be the same, but the spin quantum number has to be different to obey the Pauli principle. Okay, so you have those energy states you can just borrow them, and for each energy state you put 2, you can put up to 2 electrons. So this is due to spin degeneracy. Okay, so you have I don't know how to write this symbol like this. Maybe this is 2 in this case. Okay, now this is a factor which is so important and very easy to miss. And if you miss this again, you have a very funny result later. Okay, so and now after this, you come back to here. Okay, and you basically have a lot already. Actually, this is nice. You only need this, which we derive, and you need this, which we also derived, and you can already play with this equation and get some result. So let's do that. So first, I can calculate the total number of particles in the box or in the metal. How do I do that? I need to integrate something, right? So I integrate n of epsilon, d of epsilon. Okay, and how do I count my epsilon? The lower, I go from the lowest energy all the way to infinity. Okay, and I don't know which levels will be occupied, but this will be taken care of by the Fermi function. The Fermi-Dirac function will tell me by the time I get to some sufficiently high energy epsilon, those will be empty. So this will be taken care of by F. Okay, and this is the same as you see. I want this NED, right? So N of epsilon, D of epsilon. This is the product of Fermi-Dirac times this. Okay, so this comes from here. Okay, and that's it. And you plug in this form. This is F of epsilon is this exponential term times this whole thing, and you can begin to sense that once you take this product, it can be messy. Sure, it can be messy, but not difficult. Okay, it's indeed doable here. So you have this integral that you can do, but in principle, this will give you n. Okay, what is the origin of this? What is the origin of this? Let me remind you, you might think this is magic, but again, this n in the discrete form is just sum over I and I. Right? right? This is go back to the basic really. How do we get the total number of particles? We go to do this accounting again. We go to each energy level and see how to see how many particles are there, and then we sum them up. Okay, so similarly, we have this another very basic one. How do I calculate my internal energy U? And this is sorry. It's hard to write at the bottom of the screen. This is epsilon I and I. Okay, so this is a discrete form, and for the continuum, we have this integral to worry about. So we have this integral epsilon n of epsilon d epsilon. Okay, and then just copy down everything here. You have this epsilon, this occupation function, g of epsilon d of epsilon. Okay. So here, let me quickly say that this function has a very nice interpretation. You can interpret this as the probability that a particular state, a given state of epsilon is occupied. So let me say this again. This whole thing can be, so this, let me write it here, this F, it has a nice interpretation, can be interpreted as probability probability that the energy state epsilon is occupied. Okay, so I say probability, so you will see very soon that it really has this nice feature, because this has a range. This function has a range between 0 and 1. So very, very nice. You can just think like this. Okay, so let's have a look at this function, this Fermi-Dirac. So let me write this again. This Fermi-Dirac is 1 over exponential okay. Now, as I say, it has, this is the range. So this is Fermi-Dirac. So this is plotted in a funny way. Okay, this is plotted against the argument of the exponential function. Okay, I will show you another plotting later. But now let's look at the vertical axis, and indeed the range is from 0 to 1. Okay, so a few observations. At any temperature, at any T, if you set mu equals epsilon, that's to say, if you look at the energy level at the chemical potential, you get precisely 0.5. Okay, so this F is precisely a half at epsilon equals mu. Okay, so this is 1. And another thing is at precisely 0 temperature. This is a very interesting function. And you can already see this is a step function. But at t equals 0, mu has a spatial name. So this mu, chemical potential, is also called the Fermi energy. Okay, so if you pick up a solid state physics textbook, you will see a lot of Fermi, a lot of terms with Fermi's name attached. For example, Fermi energy, this is one, Fermi momentum, Fermi wave vector, Fermi temperature, and these are all related to this this statement here. Okay, so first let's convince ourselves that this is indeed a step function. Now, if you go above the Fermi energy, okay, now this is at 0 temperature. If you go above the Fermi energy, so this term is positive. Okay, so in this case, this exponential epsilon minus epsilon f kBt, and this will go to a positive infinity, right? You have t equals 0 here. So this is positive infinity. And therefore, this goes to 0. Okay? On the other hand, if you are below the Fermi energy, you follow all this, you have e to the minus infinity, this is still 0. And in this case, this Fermi function goes to 1. Okay, and therefore you have this step function. And you can, for non-zero temperature, you can try to plot this. You get this kind of smearing of the Fermi function, but you still have 1 when you are far below the Fermi and the chemical potential, and you have something that looks like this, looks like a exponential tail when you are far above the chemical potential at any finite temperature. Okay, then now the natural question is, what is the meaning of this? Okay, the meaning is following. Okay, let's look at t equals 0 first. So at t equals 0, what is the meaning of this? You have this step function, you have this Fermi Dirac, you have a step function like this. Okay, so this I will just I use the same notation, okay? And this will be when they are equal, so you get 0 here. Okay, so you can look at it this way. At t equals 0, the electrons will occupy the lowest energy states available to them. Okay, so it's a bit like, you can think of it this way. I give you all the energy levels. Okay, so you go from the lowest energy and you start to put your electrons. You put in the electrons, 2 electrons in a given level. And then you keep working your way up towards higher and higher energy until you use up the electrons. Okay, so if you turn this around, this is the pictures you have. You start from, if you go this way, you are at lower energy, and when you increase the energy, you are going this way, right? So what you are really doing is you are putting in electrons. So these energy states have 100% occupancy. So the probability of finding these electrons in the state lower than some threshold is 100%. The probability is 1. Okay, and this is when you use up the electron, and above a certain energy, mu, you will have no electrons at all. Okay, so in this sense, you can also think of it. You can also think of this zero temperature mu, the Fermi energy, as the energy between the occupied and the unoccupied state. Okay, so this is this notion will give you the picture of the Fermi surface later. Okay, so now the question is, what is this? What is this Fermi energy? How do you calculate this? So at zero temperature, this is really the Fermi energy. Okay, let's do that. Let's calculate this Fermi energy. Okay, so first, I know the total number of electrons is fixed. If I have a metal, if I know how many electrons are donated by each atom, the total number of electrons is fixed. It's a huge number, but it's fixed. Okay, so let's just copy down the equation first. I will have this. This is what I wrote a while ago. And from this equation, I can really account for everything. Okay, so the next line is also the same. This is a Fermi function. And then this GEDE. Okay, this is general. But at t equals 0, I'm going to do something else. So at t equals 0, I'm going to break this integral into two. I can do integration from 0 to Fermi energy, and then from Fermi energy to infinity. Okay, and then I have the same. Okay, so the first integral, I have 0 to EF, and I have this function, which is a step function. So I have 1 below the Fermi energy, right? This is the meaning of below the Fermi energy. And then I have the other one going from EF to infinity. And above the Fermi energy, I have 0 for the Fermi function, 0 times G of epsilon D of epsilon. Okay, and at least I simplify something, but I still have to plug in this G of E, D of E from here. This whole thing here. Okay, not too difficult. Let's just do it. Remember, there's a tool here. There are different ways to present this, but just first, I will do once, and you have to do it yourself. Okay, important calculation. So what did I want to do? Okay, I want to do this 0 to the Fermi energy. And this 1 is just 1, I don't care anymore. And this G of epsilon, taking into account of spin degeneracy, I will have 4 pi V H cubed times M, 2M square root of. Okay. This is copy and paste from before. Okay, now usually, remember, what is this n? This n is not the number of states. Be careful, this is the number of electrons. So that's why this 2 is here. Okay, just in case. In case when you revise, you are lost. Okay, this is due to spin. Okay, so what we want is the number density. Little n is defined as the total number of electrons divided by the volume. You see, you have a volume factor here. Okay, so what do I have? I will have 4 pi divided by h cubed Planck constant, and then I have this 2m, that V goes to the other side. This is N, this is big N. So V goes to the other side, this 2m, I combine with this. So I have 2m, 3 half, right? So I have 2m, I have another 2m here. So I have 2m to the power of 3 halves. Then I have this epsilon, square root of epsilon. I integrate, I will have another 3 half. This is a usual presentation. I can combine these two later. Then I have this. And I integrate. This is a definite integral. I evaluate this at the limit. So I have epsilon or EF here. Okay, I mean the same thing. Okay, so I'm sorry. I keep switching epsilon and E, but I meant the same thing. Okay, and minus 0. Okay, so the Fermi energy, this is what we're after, the Fermi energy. You have this N here, you have everything here, which you can rearrange. Okay, so the end result is something like this. You have h squared divided by 2n, and then you have this vector here, n. Okay, and I don't quite like Planck constant. I much prefer the reduced Planck constant. So this is personal preference because this is something I'm used to. Okay, this is a famous result. So the Fermi energy, it makes sense too, right? Look at this picture. Okay, I gave you this picture and I told you how to interpret this. So if you have the same energy levels, how do you have a system with a higher Fermi energy? So the way you need to have a higher energy is to have more particles, right? So if I have more particles, and if the volume is the same, which is something we implicitly assume, otherwise the discussion will be difficult because I want the same energy levels. Okay, same energy levels. I solve my Schrodinger equation. I have my energy levels. I give it to you, and I say, okay, I want to engineer a material with a higher Fermi energy. And then you come back to me and give me a proposal, and you realize you don't have much freedom to adjust. The only thing you can do is to try to free up more electrons into the system. That is to say, you make you create more conduction electrons, and these conduction electrons contribute to N, and V is the same. So when you have larger capital N, you have larger density N, and that is the way that you can boost the Fermi energy. Okay, so this has to make sense, but it doesn't go linearly. It goes with this kind of power. Okay, so this is good. Let me box it for you, and this Fermi energy. Okay, I want to start to do periodic boundary condition soon, because then I can teach you how to think about this in a different way, or in a way that solid-state physicists like to think about. Okay, so here you realize we have a problem that we only worry about the kinetic energy, right? So when we solve this particle in the box problem, we only have the kinetic energy, and the kinetic energy is h bar k squared divided by 2m. Okay, and now if you look at this expression, and you can kind of identify something, right? So these are all constant, and if I can define a Fermi wave vector kf, then I can associate it with this expression, the Fermi energy. And therefore, if I look at this expression, I can associate some characteristic k, which correspond to the Fermi energy, and I will call it kf. Okay, and this turns out to be 3 pi square n raised to this power. Okay, now this is nice. Okay, I want to give you this picture soon. But now let's look at the dimensionality. This also makes sense because remember this n is little n is big N divided by volume, and you know this has to be correct because what is the unit of kf? What is the unit of k? Now k is some kind of wave vector, wave number. In 1D it will be wave number. Okay, so this has the unit of 1 over length. This has the unit of 1 over length. And on this side, you have volume here. So you better have the factor of 1/3 in order to give you this 1 over length. Okay, sorry, I make a mistake, but nobody picked up. Here, this is kf square. This is kf square. So this is 1 here. Okay, so this is kf square. Kf square. So this is kf raised to the power of 1/3. Okay, so I have this volume here, so I have to raise it to power of 1/3 in order to have the unit of 1 over length here. Okay, so the unit here is 1 over length. Okay, is it okay, guys and girls? All right, so now I made the mistake, I fix it here, so just be careful. This has to give you the unit of 1 over length. Okay, so in order to attach meaning to this kf, I'm going to come back to here, but I want to, I need more terminology, and that is the notion of k-space. And the fact that you have this kf having the unit of inverse length will allow you to understand why this is also called the reciprocal space. I won't say too much about this because reciprocal space is a powerful concept in solid-state physics. This is something you will do in solid-state physics course. You will start by discussing the crystal structure in real space. Real space is the space we live. It's a space where you measure length in meters. Okay, but to treat solid-state physics problem, is useful to consider the inverse length space, and that is why there's machinery for you to transform from the length to inverse length, and this machinery is nothing more than just a Fourier transform. Okay, and now I would just assume that I would just cut through those. There's this part of solid-state physics is fascinating, but no time to talk about. But I would just immediately jump to a space spanned by kx, ky, kz. Okay, and next year, if you take solid-state physics or you have taken solid-state physics, this should make a lot of sense to you. Okay, and make sure you maybe you remember me. Okay, when you see this picture of case reciprocal space, you say, ah, we already covered this. Okay, so this is k-space. Okay, so I would just call this k-space, and I would develop this for you. So I want to discuss this problem in a space not measured by Cartesian x, y, z, but I want kx. Sorry, I want kx. I put kx here. Just kx, ky, and kz here. Okay, and then I want to on this space I want to describe my Fermi surface. That is why I want to develop this picture for you. Okay, let's get started. So the machinery is like this. You solve the particle in the box problem again. So you have this particle in the box, and this particle in the box is a three-dimensional box. And as usual, we want to start from 1D. So let's just look at 1D, and then I will just write down the 3D solution. So in 1D, what I don't want now is to have this box boundary condition. That is to say, my wave function has to be 0 at the endpoint, right? This is how we did it a few weeks ago. What I want is to eliminate this boundary by assuming that when my particle travels to this side, to A, it comes back to 0. Okay, so I want to eliminate this boundary. This is one way to look at this. Another way to look at this is you take this like a stem and then you put it on this side and just keep going forever. So the particle can travel continuously from 0 to A, and this is 0 again to A, and this A is 0 again, so you keep going. Okay, so essentially this is the traveling wave solution. It's not the standing wave solution like what you saw before. Okay, so in 1D, how do I write the standing the traveling wave solution? I will have psi of x will be A, some normalization constant, e to the I, kx times x. Okay, so this is x direction. Okay, so in 3D is vector r, and this is a vector. Then I will have some maybe different a, it doesn't matter. I will have e to the I vector k dot vector r. Okay, and then my k, vector k will have component kx, ky, kz. Okay, so that's why once I solve the 1D problem, you can just copy the rest. Okay, the boundary condition demand that when I get to A, I have to come back from 0. When I go like this, and somehow magically I come back from here. So this is the periodic boundary condition, and it's written like this mathematically. Okay, so this is periodic BC. Okay, the only difference mathematically between this condition and the box boundary condition is back then you set this to 0. Okay, this very small step means the whole difference. Okay, here we don't demand that. Okay, you plug this into here, A cancel, right? You plug this into here and you get e to the I kx A is 1, right? The other side is e to the I0, so that's 1. Okay, how do you satisfy this? To satisfy this, you have to have kx times A to be some integer multiple of 2 pi. So this integer, I will call it n, x. I will put this x here, just to remind you that we are in the 1D case. But if you look at this, your nx now can also take 0, right? If you set it to 0, you also have 1, no problem. If you set this nx to minus 1, minus 2, it's also okay. You will still satisfy this equation. Okay, so here this is the key difference between this problem and the box boundary condition. Box boundary condition, your n cannot be 0, it has to start from 1. Right? Because you have this sign wave function rather than exponential traveling wave wave functions. Okay, so I will write it in I would just write it like this, more compact for you. So this is nx times 2 pi divided by a, where my nx will be 0, plus or minus 1, plus or minus 2, and so on. And I hope this minor solution should not make you too uncomfortable, because now I have traveling wave solution. In principle, I need to be able to have a mechanism to discuss the wave which is traveling along the opposite direction, and that rho is provided by the minus integers. Okay, so I can travel towards the right. I should be able to travel towards the left too. So I need to allow for this situation. And therefore, if this is this problem is completely the same in y and z, so you will have ny and nz, and each of them can independently take this integer. Okay, so now I can write my kinetic energy, and I will use h bar rather than h. So I will have k squared, right? This is the way to write the energy, h bar squared k squared divided by 2m, and k squared is the square, the sum of the square of the component. Okay, so each of these will take this form, but I just have to change these ends. So I will have h bar squared divided by 2m, and then I have this 2 pi a, which is a common factor, 2 pi a squared, and then I have nx squared, ny squared, and nz squared. Okay, so I can just stop here actually, but I'm going to do one more step. This is a service for you. I'm going to convert to h, the Planck constant, rather than the h bar reduced Planck constant. So this will be nx, ny, and nz. Okay, so just to remind you, this is periodic BC, and nx, ny, y, nz can independently take these integers. Okay, in different color, I'm going to write you what we learned before in the box boundary condition. In the box boundary condition, you get epsilon, energy, yes, is epsilon. It's h squared divided by 8ma. And then you have nx, ny, and nz. And not surprisingly, you have different prefactor here, but that's okay because the way you count your n's are different. So this is the standing wave solution box BC. And here your nx, ny, and z can independently take the integer +1, +2, and so on. Okay, and then remember back then we call this sum of integers r squared. Okay, we can do the same, and then you will realize, although you have difference here, but once you calculate the number of states available to you below a certain energy threshold, you get the same answer. Okay, so this, did I copy? No. Don't know why. Sorry. Okay, it's here. Okay, so back then we calculate, we call this whole thing, we call it R squared. Okay, we are going to do the same. I won't do this again, but I already give you this. So I can ask myself, what is the number of states below a threshold epsilon? So this is some kind of threshold, and you know, I would like my threshold to be the Fermi energy later. Okay, but I will just use a generic symbol here. So how do I do that? I will have this number is G, and it turns out to be related to the volume. Okay, and now it's a volume of sphere center at the origin. Okay, I will write this first. So this will give me 4 pi over 3. So this is the volume of the sphere. And this sphere is the n sphere. Remember, we did this. And then I just rearrange this. This is a epsilon here. So I will have 2ma squared times my epsilon divided by h squared and raised to this power. Okay, now if you do it here using this, remember you have to take into account that because of the constraint on n, the sphere I draw will have to be divided by a factor of 8 because I am only allowed to look at the n sphere in the positive octant. And now you can have the entire n space. Okay, so your n can go to a negative direction for all three, along all three directions. That's why you don't have this 1/4. But if you do it like this, this result is actually the same as this. So this is where the two different approaches converge. So this is the same as the result obtained if using box BC. Okay, so I will give you this. This is something we summarized before. Look, I told you, right, before you have this 1/8 to handle. This is the box boundary condition, and this is the result you get, and this is identical to the form I just derived a while ago. Okay, so these are from chapter 10. Okay, so what is the next slide? Okay, I'm nearly able to discuss the Fermi surface. So what about we take a break now? A 5 minutes break, and then we'll come back and I will begin to extract the result from here. Okay, so now it's 1:30, come back at 1:35. Thank you. Okay, let's continue. Okay, so we have obtained this result, okay, 10.8, which is the same as the new result we we got from periodic boundary condition. Okay, so the next thing, which is the same question we asked before and we can ask again, is what is this product? This is GK, DK, right? This would be some number as well, just like before. So this is the number of states between K and K plus DK. And if we use the periodic boundary condition, we will get this result. Okay, so you know already from assignment that this is sensitive to the dimensionality of the system. Okay, how do you calculate this? The standard way is to recall that you have a lot of K points. Just like you have a lot of N points, this N runs to a very large number. And how large, this is something, actually we estimated that before, right? We put in a room temperature, put in the mass of some particle, you will see this is a huge number. Okay, so if we have a huge number of K points, and to get this, we usually consider a very tiny shell of a sphere. Okay, and this shell will have surface area 4 pi K squared. And in order to have the volume, we assume this sphere, we assume that we can look at another sphere which is slightly bigger, and that slight the slight difference is dk. Okay, so we have a surface area times some kind of thickness along the radial direction, and this will give you the volume. Okay, and then you divide by volume of the unit cube in K space, and here this is 2 pi divided by A. Okay, so this is the periodic boundary condition. Okay, I want to say a little bit more how to get this 2 pi divided by A. Now the easier one is to consider the 2D analog. The 2D is easier to draw. So if I am 2D, this is kx, ky. So I will have all these points. They are valid k points. Okay, so I will have a lot of them. So I will draw a few for you. Okay, and so on. How do I get this 2 pi over A raised to the power of cube in 3D? So in 2D, we are talking about an area. So that should be 2 pi divided by A times 2 pi divided by A. Okay, so this is kind of easy, but it's worth considering this a little bit deeper. So what is the distance between the adjacent points? So the distance between the adjacent point here, if you look at this, sorry, I'm going to go up by 2 slides. If you look at this separation between K, here, a little bit up, maybe I mess up this, right? So the separation between the adjacent point is when you let n to be some number, and the adjacent point will be this n plus 1. So the separation is 2 pi over A. Okay, so I will have 2 pi over A here. Okay, and I have the same for the other direction. So for here, for example, I will also have 2 pi over A. This is also 2 pi over A. So the area of this square will be 2 pi over A square, right? So this area of the black region is 2 pi over A square. Okay, now I would like your contribution. In this area, how many points do I have? How many K points do I have per 2 pi over A square? Okay, in this area of 2 pi over a square, how many k points do I have? So just the quick answer, please. Let me know on the chat. Really? Okay, let me rephrase this. I give you this area of interest, which is this area is 2 pi over a times 2 pi over a is in the black region. And how many points, how many k points does this area contain? Okay, I get the two answers that I expect, but now I want to see who wins. Any more? Is it okay? Just guess then. Let me see how. Okay, now the answer is 1. So this is important. Otherwise, you will not be able to count this. Okay, now the area is this area contains 1 k point. Okay, now remember this goes to infinity, or this goes to infinity. Actually, this is nice things to teach you now, because in solid state physics, chapter 1, you have to do something like this. So there you have this equally spaced points, and in solid state physics language, this is called a lattice. Okay, so if you have a lattice, it's very common to ask you for a unit cell, how many lattice points do I have? And this is only 1 point, because this particular point is shared by 4 unit cells. So you can only count this as 1/4. So you have 1/4, 1/4, 1/4, 1/4. So this is altogether 1. Okay, so a trick that I like is to just bear in mind that you have translational symmetry, which means you can move this unit cell any way you like, and you should still be able to describe the entire 2-dimensional space in this case. So I can, for example, move this square here. Just by translation, I don't change the size. And this is obvious that this unit cell contains only 1 lattice point. Okay, so this contains only 1 k point. And as long as you have lattice point on the edge, on the corner, you need to be careful. So a trick which I use to teach my student is to take this unit cell and displace to a location where you don't have any points or any atoms lying on the edge. Okay, so this is 1 k point per unit area. And you can imagine in 3D, if I repeat the same thing, I will have 2 pi over a cubed, and it will also contain precisely, this volume will also contain precisely 1 k point. Okay, so this volume contains precisely 1 k point, and this is the volume of this infinitesimal shell. And therefore, if I just divide this number, I will get just a pure number. Okay, so in 3D, you get this. And now, if you repeat the same exercise for GK, DK, again, this is in 3D, but I want to do it in box boundary condition. There, you remember, whenever you talk about a sphere of some surface area 4 pi k square, you need to slash it by a factor of 8, because you only allow the positive quadrant. Okay, so you have the same thing here. You have the same thing here, but it has to be slashed down by a factor of 8. And I don't want to do it here because you did it in your assignment. There, you can repeat the same thing. You can also use the K language, but because your N will have different spacing, this is the result. The spacing is pi over a rather than 2 pi over a. raised to power of cube. Okay, so you put this 8 down here and then put it inside here, you get exactly the same result, which is another thing reassuring. So 2 pi over a. So this is box BC. So this is another thing which is the same. Okay, so the purpose here is to convince you that I can think a bit differently. So whenever we teach solid state physics, we like to start here, like this, periodic boundary condition. But usually this is a later course. This is the earlier course. For the earlier course, we want to be able to link better to quantum mechanics you learned before, and therefore we usually start from the standing wave solution. But the key point is, whatever the boundary condition you use, we better reach the same outcome. Okay, so now they are the same. So I'm going to box 1 for you. Actually, I'm going to rewrite for you. And this is the 3D result, which is very important. dk 2 pi over a cube. This result is a good starting point for you to get G of energy times D energy. How do you go from here to here? Now, if you know how to derive this quickly, and you can get this also very quickly, you don't need to repeat too much. Once you know this result, this is almost coming for free. Why? You just you can get this result, can get this by putting in the dispersion relation. This is called the dispersion relation. Okay, now if you know for your problem, for each case state, you can relate an energy state by this equation. Then you can simply change a variable. Okay, whenever you see k, you change to e, and this will give you, and don't forget this dk. Whenever you see dk, you change to de, you rearrange, you get GEDE. Okay, try, you get this. But why do we want to do it this way? Why is this more powerful? So this is more powerful because you can do it this way, and you can also use a different energy spectrum, right? This is the energy spectrum telling you the momentum. Telling you the kinetic energy of a massive particle. Suppose I have some other excitation with governed by different dispersion relation. I can have something like this, for example. I can have a linear EK, which looks a bit like light, okay, like photon, okay, and I have some speed, which is governed by C. I don't want to just say this is speed of light. For example, in phonon, this will be the sound velocity. Okay, and once I plug this in, I will have different way to get my GEDE. Okay, so these are the energy versus momentum relation for specific applications. Okay, so I will just bracket this first. And if I can cook up some other way to write my energy dependence on my K, I can have different expression. Okay, so now I can draw things for you. I will draw my K space again. So after this treatment, you know, I can measure my I can have a K state that goes from minus infinity to plus infinity along all three directions. Okay, so I draw a few. And therefore, when I look at this EF expression I have earlier, h bar square kf square divided by 2m. This kf will be a radius in k space. Okay, so I just imagine this to be a sphere. Okay, so I can have a sphere in my k space, and I will be able to define a radius which correspond to kf. Okay, now you can imagine this problem to be very symmetrical, right? Because this, if I write the E again, E is h bar square divided by 2m. I will have my kx square, ky square, and kz square. Right? So I will start from the lowest energy level and start to fill up the electrons along the higher energy direction. Right? So I can have my kx equals 0 to begin with, and the next one can be nx equals 1, 2 pi over a 0 0, and then nx equals -1, 2 pi over a 0 0, and then I move to ky, and then keep kz and kx 0, and I move to kz and keep kx and ky 0. And once I do it for a lot of particles, I will end up having a sphere. And that sphere can be described by a sphere with a radius of kf. Okay, so everything we derived before can be interpreted this way. Okay, so now I want to show you another way to get the same result. So what I want is to give you this. So just let's have a look at this expression. This kf, which I quoted earlier, I want to do it a little bit differently. Okay, so how do I get the same kf result? This kf is 3 pi square n over v raised to the power of 1/3. Okay, just in case you don't believe me, let me write it for you first. So I want to get this ks cubed. Let me put it this way, it's easier. N divided by v. Okay, I derived it for you earlier, but here I can, with this picture, I can do it differently. How do I do it? I will just argue like this. I have a sphere. Okay, so this sphere will have volume. Okay, listen carefully. So I have a sphere of kf, and this sphere will have a volume of, 4 pi kf cubed divided by 3. Okay? And I know for each k point, it occupies a volume of 2 pi over a cubed. This is the argument I had earlier. So I know there are so many k points, and each of them can take 2 electrons. And I'm already at the Fermi wave vector, which means I use up all electrons. So I have to equate this to n. Okay? So now you rearrange this, you get this expression. Okay? This is the volume of the Fermi sphere, and this is the volume occupied by 1 k point. So this divided by this tells me how many k points I have. And each k point is one valid energy state. And because of the spin degeneracy, I can put 2 electrons there. But this is a F, which means I used up all electrons. So I have to equate this to the total number of particles. And rearrange this, you will get kf cube. Kf cube is already written here. You have your 3 pi square n over v. You already have this n here. This is a cube is v. You can move it here and then just kill some pi and some 2, you get this. Okay, so this is nice, and we indeed get this behavior. All right, so this is a Fermi surface, and this is kind of my favorite part. This is what I drew, but I get it from an article which is better, and this is what happens inside. Okay, Fermi surface is a surface that separates the occupied state from the empty state. Okay, and this is a textbook example of a free electron Fermi surface. Free electrons because the electrons are not interacting with each other, and they do not interact with the lattice either. So it's like a gas. That's why we can only we can get this result. This very spherical case. If you interact with the lattice, you have other potential term to consider in your Schrodinger equation, which we did not have that. We have a particle in a box. Okay. If you have those situations, solid state physics course will tell you why the Fermi surface can have all kind of shape. For example, the most spherical one is probably sodium, potassium. You get rather spherical Fermi surface. And don't worry about this kind of box. And how to get the shape of this box. This is, by the way, this is called Brillouin zone. This kind of box is called Brillouin zone. This requires some knowledge of crystal structure and the reciprocal space. But you can imagine in real life, if all Fermi surfaces are like this, they would be very boring. So my group measures the Fermi surface. We measure the size and the shape. We have a way to do it in the lab. And this is one of our recent paper, which I'm very proud of. My former PhD student did a very careful study to measure this kind of Fermi surfaces in the lab. Okay, so here, the take-home message is the following. From the textbook treatment, you need to know how to get this spherical Fermi surface. And at the same time, you need to be aware of the fact that suppose you read some research article, don't complain that some Fermi surfaces are not spherical. Most of the time, they are not, because there are other complications due to the interaction with other degrees of freedom. Okay, for example, I can even have a slightly more complicated situation where I have a quasi two-dimensional system. So in that case, the Fermi surface looks a little bit like this. It will not be spherical, but it is a little bit like a cylinder along the third direction. Okay, but in plan, they are more or less like a circle. Okay. Next, we need to have some sense about this treatment. So let's go back here. Let's write it here. Okay, how big is this EF? This is a very important number that we need to keep in mind. So here it's not sufficient to say to just keep a symbol, because we can actually do quite a bit of estimation. You will be asked to do it in the assignment. So how do we do that? We need to first get the number density. So this is the number of electrons per unit volume. Okay, and you can look up a textbook, or you can try to memorize it. So if you take so the usual rule of thumb is this: if you take a piece of solid, a piece of metal, which is 1 centimeter by 1 centimeter by 1 centimeter, you have roughly Avogadro numbers of atoms. Okay, so if you take 1 centimeter by 1 centimeter by 1 centimeter, you have that many number, Na number of atoms. Then the next argument always goes like this: how many free electrons do I have? That depends on how many electrons can be donated by each atom. So usually this is a number of the order of 1. Okay, if you have monovalent, the donation will be 1 electrons per atom. Okay, you can have trivalent, okay, 3 electrons per atom. Okay, so if you look up this table, you get this number, but here I want to give you some feeling on how to do this kind of estimation. Okay, so in the end, you get about, now, as I say, you get about 10 to the 22 to 23 number of electrons, right? There's a factor of 2 or 3 in front, doesn't matter when you compare with order of magnitude, divided by 1 centimeter cube. Okay, this is how I remember. Okay, so this, let's say, if I convert to meters, this will be roughly 10 to the 29 or 30. Let's say 29 to 30 meter cube, right? I have to add 6 here. Okay, so this is a typical number density. And then Kf, and if you look at the expression of Kf, you have a factor of 3 pi squared. This is again of the order of 10, that kind of order of magnitude. So Kf is usually of the order of 10 to the 10 per meter. Okay, and plug it in, you put in your H bar, you put in the mass of the electron, you get about 5 eV. Okay, and let me tell you this much, this 5 eV is huge. And we need to know this to proceed from here. Okay, this 5 eV is huge, and you can see this is a realistic calculation. This is about 5 eV here. And why do I say 5 eV is huge? Because let's convert this to a temperature scale. So if I just want to use a temperature scale to understand this 5 eV, I can define a Fermi temperature. And you will see this Fermi temperature corresponding to 5 eV. This Fermi temperature is about 5.8 times 10 to the 4 Kelvin. Okay, so this is huge. Again, this is huge. Why? Huge compared with what? Huge compared with any practical temperature where we do measurement on our solid. Okay, so that is to say we are not going to raise the temperature of our material to this kind of temperature. It will be melted long before we reach there. Okay, so this energy scale will offer some nice approximation. Okay, this will come up soon. Before I do that, I want to introduce another Fermi parameter, and that is the Fermi velocity. Fermi velocity is defined like this. I have the mass of the electrons times the velocity. This is how you define momentum. The other way to define momentum is to multiply this Kf by h bar. Right? I use Kf. Okay, this Kf. And if you plug in the numbers, you will find this Fermi velocity. So this is Tf. Tf is about 0.01 times the speed of light. It's about 1% of the speed of light. Okay, this is another way to remember these numbers. Okay, and now I will begin to tell you why these numbers are important to make progress. The way to think about this is to look at this formula, this graph here. This is from your textbook. Okay, so these numbers are typical, right? Typical number. You might have a system with a little bit lower, a little bit higher, but this is, after all, this is order of magnitude type of estimation. Okay, the first thing is the following. If you look at solid state physics textbook, sometimes they do not even introduce the term chemical potential. Okay, and now I will tell you why. The chemical potential is a function of temperature. It can be written like this. Okay, those books, they just use Fermi energy. They don't separately introduce chemical potential. And the reason is here. You have pi squared divided by 12, kBt divided by EF here. Okay, or I can change this EF to kBTF and cancel kB. Okay, the reason is now clear. If I'm at zero temperature, this term will be gone. So my chemical potential at zero temperature limit is strictly defined as the Fermi energy. Okay, this is what I said before. But then, if your Fermi energy is so huge, and if you are doing solid state physics, let's say you maybe not very strict solid state physics. Let's say you are doing material science of metals, and you are not gonna care about heating your metals to a very high temperature. Let's say you are only interested in the temperature range where you can make devices. Okay, then you are after a temperature scale of the order of several hundred Kelvin at most. 1000 Kelvin is already too crazy. And you have to divide by a huge number, much larger. Okay, room temperature. So this correction factor is of the order of 1/100. And then you square it. Okay, and this is of the order 1. And this is a small number, 10 to the minus 2. And then you square it. And therefore, this correction term is very tiny. And that is the reason why you can, even for practical purposes, you can take the chemical potential of metal to be the Fermi energy. Okay, and what is the implication here? So this formula I just quote, it can be shown, but it's not necessarily easy. This is actually rather messy to get this expression. We can appreciate this by looking at this curve here. So this is something you can plot. You take the Fermi function I gave you at the beginning of the lecture, pull up your Mathematica, you can just really plot everything yourself. Now, if you plot this by fixing the temperature, and now the temperature is measured in terms of the Fermi energy. Okay, Fermi energy is let's say 5 eV. And if you are interested in the temperature, which is very low compared with Fermi energy, let's say 1% of that, you get this line here, solid line. Okay, then you basically get a step function. Really, you can try to plot it yourself. You really just get something that looks like a step function. If you don't have enough resolution, you won't even see the difference. Okay, and now I want to draw your attention to this. This is where you begin to need correction. And this is where the temperature is half of the Fermi energy. Okay, and you have this curve here. I told you the Fermi energy is about 5. I think this is the number the author used for for the simulation. So this is the Fermi energy, 5 eV. Okay, now look at this. How do I identify the chemical potential for this case? I use the definition. Chemical potential is the energy when the Fermi function takes the value of 0.5. Okay, so let's do that. 0.5 is roughly here. I will draw a horizontal line. And then I hit already this line here. Then I can identify chemical potential, which is different from the Fermi energy. So this is the chemical potential for this case, the one with the cross. Okay, somewhere here. Okay, you can see the difference. This is the chemical potential mu is you can see that is clearly different from 5 eV, and it's lower than 5 eV, and this makes sense because of the minus sign here. Okay, so from here you can know what happens when the temperature is higher. Okay, and how do you interpret this kind of finite temperature dependence? What is the next? Let me see. Okay, this is when we can begin to, this question I ask, how do you interpret the finite temperature Fermi function, is related to how we solve this heat capacity problem. Okay, so let's look at this. If I have this finite temperature, at zero temperature, I have a step function. At finite temperature, I have this smearing, right? So now I plot energy. This is 1. And as I say, I don't want to worry about the difference between chemical potential and Fermi energy. I'm going to assume a temperature which is not too high compared with the Fermi energy. So I will have some kind of smearing. This is a half, 0.5. This is 1. This is a half. This is 0. So I have to cross here. I want to draw it a little bit dramatic for you to appreciate this. If you look at this figure I gave you earlier, this one, you can kind of, another information you can extract is this smear region. This smear region is of the order of KBT. Okay, so if the KBT is very small, this region will be very small. When KBT is 0, this region is completely sharp. Okay, so we can kind of think of it, this is just order of magnitude. Again, there can be a factor of 2, depends on, it's not important for the argument. Okay, so you can think of it like this. When you are at finite temperature, only the states around, only the states within KB times T of the Fermi energy will be affected. So if I look at an energy state very, very far below the Fermi energy, those are basically sitting there doing nothing. It will not be affected. These are locked. These states are locked by the fact that you have a Fermi function. Okay? So if I inject some energy into the system, a lot of states occupied by the particle will not be affected. They cannot absorb because they are too far. And to absorb, once the particles, once a fermion absorb, they have to be able to go somewhere. And if you are here, these are, let's say if you are here, these are completely locked because if you draw a KBT, this state is occupied. So it cannot go there. So the way to free up those electrons after you inject this KBT of energy is for those most energetic one to go beyond the Fermi energy. Okay, and this is called the Fermi surface effect. So I hope you can appreciate why we need to measure the Fermi surface, because this is this really determines the thermal property and also the transport property of metals. Okay, now we can look at the heat capacity. You can already have the clue, right? Why is the heat capacity in reality is so small compared with the estimate from the classical model, classical statistics. Okay, the heat capacity is defined by, I would just use the total differential, right? I would just look at it as the change of the internal energy in response to the change of the temperature. Okay, so I can use my zero temperature as a reference. Okay, and this is T minus 0. Okay, so we can actually do this analytically, but this will be rather difficult, and you will get a result which is only a little bit more accurate. So to get the physics out, I will just do it using the graph. Okay, so I'm going to look at this picture here and explain to you how to do things. Okay, first I'm going to just calculate how many electrons are affected once I inject the thermal energy of KBT. Okay, how many electrons are affected? First, I need to calculate how many, I need to be able to calculate the number of electrons. Okay, the number of electrons, the way to calculate is as before, we do this integration, right? GEDE times the Fermi function. Okay, and this will give me the number of electrons. And how do I draw this picture? Okay, so let's first estimate the number of electrons at zero temperature limit, and this is kind of easy. I will still have the product of these two functions. So this G of E goes like that. This is a famous square root of E dependence. That's why you see this curve here. Okay, I'm going to take you step by step. Okay, so this is G. This is G, the density of states. Okay, and I want to multiply by the Fermi function, and that is why you see some curve here. So at zero temperature limit, the Fermi function is a step function, right? So I have to multiply by a step function that takes a value of 1 and 0. Okay, if I multiply these two, I will get a curve like this. So below EF, I've just multiplied by 1, so I just faithfully trace this curve. And once I reach EF, I have to kill everything, so I have to multiply everything by 0, so I basically have this curve. Okay, so this A is actually this area. This is the product of this Fermi function times GE, and then I integrate with respect to energy, and I will get this area. So this tells me a number, the number of particles at zero temperature. Okay, another one is the finite temperature. The finite temperature, unfortunately, in that case, I don't have a step function, but I will have a slightly rounded curve. So what I have then is the same expression, but I will, as I say, I will do it graphically. So I will, far below the Fermi energy, I still have 1, so I still trace this curve quite faithfully. Then around the Fermi energy, I begin to have rounding, so this becomes to get smaller. So for this curve, I have to multiply by a smaller number, a number less than 1. So basically, I just magnify like this, negatively, okay? And then I will reach Fermi energy. Now, this is my Fermi energy. And above Fermi energy, I will have something which is non-zero, but smaller than 1. So I have to take this curve and then multiply by scale by that factor. So eventually I get this. And that is this dashed line here, okay? So this function, again, I do integration, I will have this. This is A prime. Okay, so this is A prime, is this area, DE. So to make you understand this, I'm going to say this is T equals to greater than 0. Okay, so if you look at this figure basically condenses these two pictures. What it wants to say is when you are far below the Fermi energy, you don't see the difference between the two. So all the difference are happening around KBT, around EF, within KBT. Okay, so the difference between these two areas will tell me the number they are affected. Okay, the difference between these two areas will tell me the number of electrons that are affected by the injection of the thermal energy. And this area can be approximated by just a rectangle with the width of KBT. Again, area on this kind of graph tells me a number. Okay, I can just approximate the difference as a rectangle. Okay, so now I can write the number of electrons affected. So the number of electrons affected by the injection of thermal energy is roughly this area, which is kBt times the width times the height. What is the height? The height is g, this function, the height, I can read it here, is g of EF. Okay, so this is a number. And each of these electrons, can take this energy kBt, can absorb kBt. Okay, so the total internal energy absorb, U total absorb, will be number times energy. So I will have kBt times kBt times G of EF. Sorry. Okay. So this tells me I will have kb squared T squared G of EF. And the electronic contribution C electronic, I just take the derivative. I will just take this derivative and I will have 2 times kb squared times G of EF times T. Okay, so this is the end result from this kind of hand waving treatment. And if you do the full treatment, by taking this integral very seriously, you get C electronic contribution to the heat capacity to be 1/3 pi square G of EF kb square times T. Okay, so the difference is this 2 and pi square divided by 3. Right? This is a very tiny difference. This is the kind of thing we cannot get from this hand waving treatment because we just assume a kBt as a width. Maybe it's slightly bigger than kBt, slightly less than kBt, and that cannot be handled. Okay, I know I run out of time. So this, just give me 3 more minutes. I will finish this. And then I will show you the midterm statistics. Okay, if we take this full expression, CEL, electronic contribution, and let's just take this as some gamma tilde. This is some number of the order 1. Okay, this expression can be rewritten like this. You can have gamma tilde, and if you plug in the density of states expression and rewrite it, you can write it like that. T divided by TF. Okay, so I can rewrite this expression like this. So this is a full answer. It goes back to the opening slide of today's lecture. Why do we have a heat capacity which is so small compared with the classical prediction? This is the answer, because your heat capacity due to electron is some constant of the order 1, times the classical. This is the classical. Sorry, I will just write it here. This is the classical prediction. Okay, and this is of the order 1. And this has to be corrected by this ratio, which is T divided by TF. And I already told you TF is huge. TF is 10 to the 4. So at any practical temperature, we will have a huge correction. And that is the reason why the Drude prediction is not correct, because that picture, the Drude classical picture, used the classical statistics. There's no notion of the Fermi surface. And the fact that you have a Fermi surface gives you this part of the physics. Okay, sorry, this is all for the heat capacity, and I will show you the statistics of the midterm, and then I will let you go. Yeah. Okay, so this is the statistic you ask. This is this year, and last year we didn't have midterm because of all this sudden shutdown. So I put the score from 2 years ago for comparison. Okay, so similar. This one is good. The maximum is 61 out of 68, 90%. And this is a rather nice bell shape. It would be nice if this can be pushed up a little bit. And the average is 54%. Okay. All right. Thank you very much.